Today we're going to talk about orthogonal sets. Let's review that y hat is y dot u over u dot u times u is the orthogonal projection of y onto u. And suppose that we have vectors u1, u2 all the way to up be an orthogonal basis for w in Rn. For each vector y in w, vector y would equal y dot u1 all over u1 dot u1 times u1 plus all the way y dot up all over dot up times up. Let's look at example 1. Suppose that u1, u2, u3 is an orthogonal basis for R3 and let w equal span u1, u2. Write vector y in R3 as a sum of vector y hat in W and vector z in W perp. So first, we want y to be the sum of y hat and z. So we know that y hat is y dot u1 all over u1 dot u1 times u plus y dot u2 all over u2 dot u2 times u2 and then plus y dot u3 all over u3 dot u3 times u3. This is y hat, and this is z. To show that z is orthogonal to every vector in W, you need to show that z is orthogonal to the vectors in u1 and u2. So we would show that z dot u1 is 0, and we know that z is y dot u3 all over u3 dot u3 times u3, and then it would be dot u1, and we know that u3 dot u1 equals 0, so that would times 0, which would give us 0, and then z dot u2 would be y dot u3 all over u3 dot u3 times u3 dot u2. And u3 dot u2 is 0, so that would make this whole thing 0. So it would be 0, and since the dot product is 0, z is orthogonal to the vectors u1 and u2. Theorem 8, the orthogonal decomposition theorem. Let W be a subspace of Rn. Then each vector y in Rn can be uniquely represented in the form vector y equals y hat plus z, where y hat is in W and vector z is in W perp. In fact, if u1 all the way to up is any orthogonal basis of W, then we have the following. The vector y hat is called the orthogonal projection of y onto W. So let's look at example 2. Let u1 be 301, U2 be 010, and U3 be 0310. Observe that U1 and U2 is an orthogonal basis for W. And span, W equals span U1, U2. Write Y, vector Y, as a sum of vector W and a vector orthogonal to W. So the first thing that we would do here is we want our projection of Y onto W, which equals Y hat. And this would equal Y dot U1 all over U1 dot U1 times U1 plus Y dot U2 all over U2 dot U2 times U2. So this would equal Y dot U1 is 10. U1 dot U1 is 10 times U1, which would be 301, plus Y dot U2 is 3. U2 dot U2 is 1 times U2, which is 010. This would equal, when I add these together, 331. And that is Y hat. Now we need to find vector Z using that we know Y equals Y hat plus Z. Therefore, we would have Z equals Y minus Y hat. So I would have Z equals 0, 310 minus 331, and that equals negative 309. Now, we need to verify that Y hat and Z are orthogonal, even though Theorem 8 ensures that, and you would have to take the dot product of those two. So I'm just going to state Y hat and Z are orthogonal because Y hat dot Z equals 0. And this would be your geometric representation of it. Let's look at Theorem 9, the best approximation theorem. Let W be a subspace in Rn. Vector Y is any vector in Rn, and Y hat the orthogonal projection of Y onto W. Then Y hat is the point in W closest to Y, vector Y, in the sense that the distance between Y and Y hat is less than Y minus V, for all V and W distinct from Y hat. Let's look at example 3. Find the closest point to Y and span U1, U2, where Y is 2, 4, 0, negative 2, U1 is 1, 1, 0, 0, and U2 is 0, 0, 1, 1. So we need to find the closest point, and that's the orthogonal projection Y hat. So we have Y hat equals Y dot U1 all over U1 dot U1 times U1 plus y dot u2 all over u2 dot u2 times u2. So this would be y dot u1 is 6, u1 dot u1 is 2, times 1, 0, 1, 1, 0, 0, plus y dot u2 is negative 2, u2 dot u2 is 2, times my vector u2, which is 0, 0, 1, 1. This would be 3, 3, 0, 0, plus 0, 0, negative 1, negative 1, which will give me 3, 3, negative 1, negative 1. So the closest point is the orthogonal projection y hat, and that would be 3, 3, negative 1, negative 1. Theorem 10. If U1 and UP is an orthonormal basis for the subspace W of Rn, then the projection of y onto W is as follows. If U are all of those vectors, then the projection of y onto W is U times U transpose times vector y for all y and Rn.